So let's look at this problem. Let's look at this problem where the joint PDF of x and y is given by 2 over x squared y squared for x greater than y greater than 1. So it's in this region. So this is the point 1 comma 1 x y, and x greater than y is this region, and x is greater than 1. So it is in this piece of the first quadrant, but here. That's where the density function is non-zero. So the problem is find the joint PDF of and the marginals. Let's say PDF of, we'll pick up one problem of the z equal to x plus y and w equal to x over y, let's say. So then we can find out also, so in other words, we want fzw, z comma w, and let's say fzz, and also fw, the marginals of each one of them. So the question is, how do we do it? So first, let's solve for x and y back. So the first step is use these two equations. So notice that a few observations even before that. X is greater than 1, y is greater than 1. So z is clearly greater than 2 in terms of the range. And x is greater than y, both are greater than 1. So w is greater than 1. So that's to start with. Maybe there are other conditions. So let's solve for x and y. So from here, x is y multiplied by w, and we substitute that into here. And that gives z equal to x plus y is y multiplied by 1 plus w. So that gives y equal to z over 1 plus w, and that gives you the x1. x1 is here. So x1 is cw, y is here over 1 plus w, and y1 is z over 1 plus w, or the two solutions, is the one pair of solutions. Now, remember, we have these conditions, but you can see there are also some other conditions because look here, x is greater than 1. So we know that this is another, and same thing here. So we also get z is greater than 1 plus w, and also from here zw is greater than 1 plus w. If you look at these two, this seems to be automatic because c is greater than 1 plus w, and w is greater than 1. So with this and this is satisfied. So we only need this this condition. So the three conditions are from here and this. So let me, in the z domain, let me draw the region where the first identify the region in the zw domain. So z here, w here. So this is 1, 2, c greater than 2, and w greater than 1, and then z equal to 1 plus w. So that line goes through this point. So this is the line c equal to 1 plus w. So from the previous slide, we have the conditions are z greater than 2, w greater than 1, and z greater than 1 plus w. So c greater than 2 to the right side, w greater than 1, and c greater than, so it will be, this is the region where the joint density function of c and w are going to be valid. So it's useful to identify that. Now let's find the Jacobian. So the Jacobian is dc by dx, this is ec, dc by dy, and dw by dx, dw by dy. So that will turn out to be, remember, z is x plus y, so this is 1, 1. W is x over y, so this is 1 over y with respect to x, and the other one is minus x over y squared. So when you take the determinant and take the absolute value, that turns out to be, you can see x plus y over y squared. Now, we want to rewrite this in terms of the roots. So in fact, this is Jacobian evaluated at x equal to x1, y equal to y. Remember, we had previously, so x1 was x plus y is z, and y was z over 1 plus w the whole square. So this turns out to be 1 plus w the whole squared over c. So we are ready to, we have everything. So we are ready to find the joint density function of c and w. That turns out the formula is 1 over Jacobian fxy x1 comma y1. So that will turn out to be 1 over, so z, 1 over Jacobian is this. And the density, I'll just write it down here. This is x1 squared, y1 squared, because that's the joint density, given joint density function. So I'm going to substitute for x1. So this is c over 1 plus w, the whole squared, 2. And x is, from the previous sheet, x1 is zw over 1 plus w, the whole squared. And y1 is z over 1 plus w the whole squared. If you simplify all this, 1 z cancels, 1 plus w squared once cancels. So you get 2 multiplied by 1 plus w the whole squared divided by z squared, and z. So z cubed, and there's a w squared here. So w squared. So this seems to be the answer. So this is good for c greater than 2, w greater than 1, which is this region, and c greater than 1 plus w, and 0 otherwise. So that's the joint PDF of z and w that's valid in this region. Now, of course, the next answer, the next question is to find the marginals of z and w. So that's an, so we technically there's nothing much. You take this and just integrate. So it's all the details. So let me try to do that just to show you the mechanics involved in that. So FCC is, so I'll draw that region one more time here. So this is 1, 2, this is 1. So the line goes through like this. So this is the region we need to integrate on. So of course, yeah, for FCC, we are going to integrate on W. So this is Z and this is W. So we'll take a strip like this, integrate here. So this is W equal to 1. This is Z equal to 1 plus W, or so this is the region Z greater than 1 plus W. This is where we need to integrate. So W goes up to Z minus 1. So W goes from 1 to Z minus 1. And the joint density function, which was 2 multiplied by 1 plus W the whole squared divided by Z cubed W squared dW. So I'm going to pull out all the z terms outside. So this will turn out to be 2 over z cubed. We just need to go through this. There's no other way. And I'm going to expand this 1 plus w squared. So this is 1 plus 2w plus w squared over w squared. Maybe you can do it by parts, but I'm going to do it this way. dw. So this, if I write it as 2 over z cubed, 1 to z minus 1. This is 1 over w squared plus 1 plus 2 over w dw. I put the middle term at the end. So if I integrate this, this is 2 over z cubed minus 1 over w plus 2 log w. From 1 to z minus 1. So let's look at the denominator, the bottom value to be substituted. So if you substitute 1 here, this becomes minus 1 plus 1, so that goes away. This becomes 2 log 1, that's gone away. In other words, the contribution due to 1 is 0. So all we need to worry is the plus z minus 1 plus 2 log z minus 1. So we can leave it like this, or let me simplify this. And how do I know this is right? So let's simplify and see whether I can check the area under this to be 1. So if I combine these two terms, the first two terms, so this comes 2 over z cubed. This becomes z minus 1 the whole squared. When I expand with this minus 1 cancel, so this is z squared minus 2z over z minus 1 plus 2 log z minus 1. So I'm going to do a little more simplification. I pull out a z and take this inside. So this is z minus 2 over z squared, because z cancels, and z minus 1 plus 2 log z minus 1. So I guess you can leave it like this, or you can cancel a z here if you wish, and write this as 1 over z squared. Write this as z minus 1 minus 1. So this is z minus 1. So this is for z greater than or equal to 2. This is certainly algebraically correct. So just to double check whether this is area under this is, so this is a non-negative density function, because you can see from here z is greater than 2, z is greater than, so this is positive, this is positive, this is, so this is all good. Now, so let's check the area of this from 2 as a check, from 2 to infinity fcc dz. So this turns out to be 2 multiplied by 2 to infinity 1 over z squared dz, which is easy to integrate, minus integral 2 to infinity 1 over z squared z minus 1. This also you can integrate by partial, plus 2 integral 2 to infinity. So notice that there is a term I missed, the c cubed. When I take it inside, this should be 2 over c cubed. This should be 2 over c cubed. So this is log z minus 1. And here there is a z cubed dz. So the first term is easy. This is 2 multiplied by 1 over minus z 2 to infinity. So that's good. I'm going to leave this term as it is, because I think this is going to cancel out here. So minus 1 over z squared z minus 1 dz 2 to infinity plus 2. Let's do this by parts. So this is du. So its derivative, its v is going to be, this is e to the power minus 3. So that's c to the power minus 2 over minus 2. So that's minus 2z squared, and the log stays as it is here. Next term is minus plus, this 2 cancels. So this becomes integral 1 over c squared multiplied by the derivative of this. So that's c squared multiplied by c minus 1. And my hunch was right because this cancels with this. And remember here the limits are 2 to infinity. Here it is 2 to infinity. Notice what happens when you put infinity, because of this grows much faster than this. So the upper limit is 1 over infinity squared is 0. That gobbles up this one. And when we put z equal to 2, this becomes log 1. So that is 0 divided by something finite 0. So this contribution is 0. Here, if you look at it, the answer is 2 over 2, because top limit minus bottom limit, that's 1. So it checks. In other words, this is 1. So this density function is correct. FCC equal to this. So finally, now we come to the FWW. So FWW is going to be, instead of drawing the diagram, I'm going to just draw it here. So we are going to, W goes from in this bed. So I'm going to take a strip like this. But this is the line z equal to W starts from z minus 1 and all the way to infinity. So I'm sorry, z. This is z. So z starts from 1 plus w. So this is the point 1 plus w, and z goes all the way to infinity. So we integrate along this strip. So that's going to be 1 plus w to infinity of the joint PDF of z and w. So that is, if you recall, that's going to be 1 plus w to infinity, 2 multiplied by 1 plus w squared over z cubed w squared dw. So I'm going to pull out all dz. So I'm going to pull out all the w terms outside. 2 multiplied by 1 plus w whole squared, w squared, 1 plus w infinity 1 over z cubed. So this is much easier. This integration is minus 2 minus 1 over 2z squared. 2 cancels. So this is 2 multiplied by 1 plus w the whole squared, w squared, 1 over minus 2 z squared, 1 plus w to infinity. So top limit is 0, minus minus goes away, 2 cancels. This becomes 1 plus w squared. So 1 over 1 plus w squared, so that also cancels. You get 1 over w squared. For w, we already saw greater than 1. So that's something like this. And just to check, this you can mentally see this is correct, because 1 to infinity FWW is 1 over w squared, 1 to infinity. So that's minus 1 over w, 1 to infinity, that's 1. So that checks. So notice that if w is here, and this is the density function of w, and so here is the density function of z, and if you take the product, you are not going to get this one, because the FZC has too many terms. So we know that in this case, z and w are not independent. See. Now, interestingly, the same problem, if you define u to be 1 over w, in other words, y over x. Remember, in the original problem, In the original problem, we defined W to be X over Y. So if you flip it Y over X, that's the same as flipping W. And we already have the density function of W. So it's very easy to do here. So W is greater than 1, so U is less than 1, right? So U goes from 0 to 1. And the solution of W is 1 over U. And the derivative of W1 with respect to U is minus 1 over U squared. So its absolute value is just 1 over U squared. So we can find out the density function of U. It's a simple exercise. So that's going to be du1 w1 by du. Remember, W plays the role of X and U plays the role of Y. So dw1 by du, dw and w1. So that's going to be 1 over U squared. And what W is here, so 1 over W1 is here, 1 over U. In other words, this is 1 over W1 squared from here. But W1 is 1 over, so this is 1 over U squared. W1 is 1 over U, so that's 1 over U the whole square. U squared goes up, so you get 1. Bottom line is U is uniform. So U, which is Y over X in the original problem, is uniform from 0 to 1. So this is the complete solution. So we have the joint density function. So just to recap, the joint density function of X and Y is in this region, in this wedge, and it is 1 over quadratic on X and Y. And in fact, X and Y are independent here. We define Z to be X plus Y, W to be X over Y, and U to be Y over X. So U is uniform. That's easy to remember. And the W and the Z is given by the complicated formula that we had a little earlier, which is here. FCC is this is the density function of FCC, and FW was 2 over W squared. FW was, I'm sorry, 1 over W squared for W greater than 1. And Z is for C greater than 2. And the flipped version of W, which is Y over X, is uniform in 0 to 1. So that's the complete solution.